This is AlphaEvolve. So I can't remember where this came up. Maybe one of our discussions or in the Slack. So this is AlphaEvolve coding agent for scientific and algorithmic discovery. So they're doing this sort of AI scientist type of thing. This is their white paper on it. So in this white paper, we present AlphaEvolve, an evolutionary coding agent that substantially enhances capabilities of state-of-the-art large language models on highly challenging tasks, such as tackling open scientific problems or optimizing critical pieces of computational infrastructure. AlphaEvolve orchestrates an autonomous pipeline of large language models whose task is to improve an algorithm by making direct changes to the code. Using an evolutionary approach, continuously receiving feedback from one or more evaluators, AlphaEvolve iteratively improves the algorithm, potentially leading to new scientific and practical discoveries. We demonstrate the broad applicability of this approach by applying it to a number of important computational problems. When applied to optimizing critical components of large-scale computational stacks at Google, AlphaEvolve developed a more efficient scheduling algorithm for data centers, on a functionally equivalent simplification in the circuit design of hardware accelerators, and accelerated the training of large language models underpinning AlphaEvolve itself. Furthermore, AlphaEvolve discovered novel, provably correct algorithms that surpass state-of-the-art solutions on a spectrum of problems in mathematics and computer science, significantly expanding the scope of prior automated discovery methods. And this is a citation here. Romera-Paredes et al. 2023. Notably, AlphaEvolve developed a search algorithm that found a procedure to multiply two 4x4 complex valued matrices using 48 scalar multiplications, offering the first improvement after 56 years over Strassen's algorithm in this setting. We believe AlphaEvolve and coding agents like it can have a significant impact in improving solutions to problems across many areas of science and computation. So this Romera-Paredes et al. Paper. So this is the Nature paper, Mathematical Discoveries from Program Search with Large Language Models. And this is their kind of approach to this. Large language models have demonstrated tremendous capabilities in solving complex tasks, from quantitative reasoning to understanding natural language. However, large language models sometimes suffers from confabulations or hallucinations, which can result in them making plausible but incorrect statements. This hinders the use of current large models in scientific discovery. Here we introduce fun search for searching the function space, not that they're actually fun. And this is an evolutionary procedure based on pairing a pre-trained large language model with a systematic evaluator. We demonstrate the effectiveness of this approach to surpass the best-known results in important problems, pushing the boundary of existing large language model-based approaches. Applying fun search to a central problem and external combinatorics, the capset problem, we discover new constructions of large capsets going beyond the best-known ones, both in finite dimensional and asymptotic cases. This shows that it is possible to make discoveries for established open problems using large language models. We showcase the generality of fun search by applying it to an algorithmic problem, online bin packing, finding new heuristics that improve upon widely used baselines. In contrast to most computer search approaches, fun search searches for programs that describe how to solve a problem rather than what the solution is. Beyond being an effective and scalable strategy, discovered programs tend to be more interpretable than raw solutions, enabling feedback loops between domain experts and the fun search agent, and then deploying such programs in real-world applications. So this is the paper here. And this just kind of describes the fun search agent and how they did this. So back to this paper here. So they actually compare fun search and AlphaEvolve in table 1. This is the fun search is their previous agent, AlphaEvolve is their new agent. So fun search does something, and then AlphaEvolve, so I guess improves upon it in some way. So FunSearch evolves single functions. AlphaEvolve evolves entire code files. FunSearch evolves up to 10 to 20 lines of code. AlphaEvolve evolves up to hundreds of lines of code. FunSearch evolves code in Python. AlphaCode evolves any language. FunSearch needs fast evaluation, around less than 20 minutes on one CPU. AlphaEvolve can evaluate for hours in parallel on accelerated GPUs. FunSearch allows for millions of large language model samples to be used. In AlphaEvolve, only thousands of large language model samples can suffice. FunSearch uses small large language models. There's no benefit from the larger models. AlphaEvolve benefits from the state-of-the-art large language models. FunSearch uses minimal context, which draws from only previous solutions. AlphaEvolve draws from rich context and feedback and prompts. And then finally, FunSearch optimizes single metrics, whereas AlphaEvolve can simultaneously optimize multiple metrics. Okay, so that's, and then this is the high-level overview of AlphaEvolve. So remember, AlphaEvolve is sort of an improvement upon their previous attempt at this. In this case, what we're doing here is we have this feedback between humans and the agent. Humans define what. The human set evaluation criterion provides initial solutions and optional background knowledge. They provide a problem definition to the agent AlphaEvolve, which figures out how. And then there's this prompt sampler, and the prompt sampler gives rich content containing past trials and ideas to a large language model ensemble. That ensemble is a proposal of improved programs that goes to the evaluators pool, and then that enables programs with quality scores and other feedback, which goes to the program database, and then those are programs that improve and act as inspiration, and that goes then back to the prompt sampler, which then provides an improved solution to the human. So this is interesting. They use an evolutionary algorithm in this orchestrating procedure. And that evolutionary algorithm gradually develops programs that improves the score on the automated evaluation metrics associated with the task. Actually, why don't we go through creative generation? So they use this creative generation. So to drive the evolutionary procedure, AlphaEvolve leverages the capabilities of state-of-the-art large language models. His principal role is to digest information about previously developed solutions and to propose new and diverse ways of improving the solutions. Although AlphaEvolve is model agnostic, in ablations we observe that AlphaEvolve performs increasingly better as the underlying large language model improves. So this is kind of their code here. This is just showing kind of the blocks here that they're using, and just kind of thinking about this and how this is implemented. Okay, so this figure 3 is an illustrative example of applying AlphaEvolve to evolving a supervised learning pipeline. All snippets of code are abbreviated with ellipses, which you can see here on the so these are just the different code snippets that they're demonstrating, indicating skipped lines. The user provided file with blocks marked for evolution and a special evaluate function that can be evoked to score the current version of the code. Example of an assembled prompt can be provided to the large language model. Example output generated by the large language model in C. So this is A here. This is what is provided by the user. So this code here is provided by the user. This code in B is an example of the assembled prompt, which will be provided to the large language model. So you have the prompt here. So it looks like what we're doing here is we're sort of annotating this and providing more detail. And then C is where you have an output generated by the large language model. So the models that they use, AlphaEvolve employs an ensemble of large language models. Specifically, we use a combination of Gemini 2.0 Flash and Gemini 2.0 Pro. This ensemble approach allows us to balance computational throughput with the quality of generated solutions. Gemini 2.0 Flash, with its lower latency, enables a higher rate of candidate generation, increasing the number of ideas explored per unit time. Gemini 2.0 Pro, possessing greater capabilities, provides occasional higher quality suggestions that can significantly advance the evolutionary search and potentially lead to breakthroughs. This strategy mix optimizes the overall discovery process by maximizing the volume of evaluated ideas while retaining the potential for substantial improvements by the more powerful model. Okay, so they actually get into their evolutionary methods here. AlphaEvolve extends a long tradition of research on evolutionary or genetic programming. Will run repeatedly uses a set of mutation and crossover operators to evolve a pool of programs. In particular, classical evolutionary techniques have succeeded in symbolic regression applications, automated scientific or algorithmic discovery, and scheduling problems. Now, the challenge with evolutionary methods is the use of handwritten evolution operators, which can be hard to design and may fail to capture important properties of the domain. In contrast, AlphaEvolve uses large language models to automate the construction of these operators. It leverages the large language model's world knowledge to mutate programs without the need to predefine a set of allowed mutation operators. So it actually mutates things using the world knowledge of the large language model, and it doesn't use mutation operators as usually would in an evolutionary algorithm. So this is so the fun search system is so fun search, which was the precursor to this model, they focused on Bayesian optimization, and in AlphaEvolve they're using this sort of evolutionary approach.